Okay. Hello everyone. Welcome to the second video of Alucard the Vampire. This is part two. In last part, or I guess last meeting, we covered the front end of the language. How the front end is really just a bunch of macros that we can just macro expand. They're not very complicated. We covered the storage mechanism. Basically, it's two hash tables. And we also covered emitting, which is we have some imperative list. We change some pointers and we build up the real body. We do this for safety reasons among common list functions. With that said, we're finally ready to kind of figure out how the language takes that form and compiles it all the way down to vamp-ir. Like we're at the point of the pipeline, as we called it. And so we're going to cover the pipeline. A quick way of figuring out where that is we look at package.lisp in any folder, and there's a thing called passes. So I assume it's there. And we can see that there's some pipeline module. And if we scroll all the way down to the bottom, we actually define it, which is neat. But I don't know, let's search for pipeline. And when you search for pipeline, you're greeted to this kind of file, which covers, kind of says some type signatures, and then gives out some functions. But this is the right way of looking at it, because before, when we were giving examples, wow, that was a while ago, I guess. We were doing we're calling pipeline. So let's figure out where it is. Call to vamp-ir, calls to primitive circuit calls this one, and this one calls this one, and this one calls this one. You can see that it's kind of layered, top to bottom like this. I'm sorry for kind of the mess, but sometimes you have to do it like this if you're wanting small passes. Okay, so it seems like the very first thing that we do is called linearize. So let's see what this linearization does. Because so far, when we just look it up, we end up with nothing, right? We have some execution body. We end up with this here, but let's figure out how we get from the frozen parts of the circuit down to where we care about. So let's look at what this linearizes. We call evaluate and cache body is the first thing. So let's, I guess, try to figure out how to call that. Let's actually call it as well. Evaluate and cache body on hashtag B67. Actually, I'll just do it this way for y'all to see. It calls it and gives us this. So what does this evaluate and cache body do? This one isn't really too immaculate. It just checks if the circuit's properly cached, which for the now, we always say no. I'm thinking of adding a caching feature, which makes it so, oh, hey, if nothing's been redefined, just spit out the same assembly. Like, why are you redoing all the assembly? But, I don't do it at the moment. So, this thing always fails. And so we always execute the circuit. So we, we execute it, we set it, and then we give it back. And by executing, all we really do is call this function, which just calls with circuit body, and calling eval in the frozen term. So this is just calling eval. We've not really done any work. We've just evaled it. And this is what the evaled form of this looks like. It looks like this mess here. We look up plane X, we exponent this thing by 2. We look up the Y plane, blah, 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 blah. There's a bunch of stuff, and this function is LP more by hand. And which you can see here that, the code isn't really complex. You're just exponenting things by 2 and then summing them. Which you can see here. Okay, so that really doesn't do anything. So this doesn't really need explanation too much. Next up, we call ANF normalized expression. So we take this. I'm going to be using hashtag V syntax from here on out. I don't want to write all this over and over again. Hashtag V means 68 is this expression right here. So just FYI, because I'm not going to write it out by hand every time. That's too tedious. The next pass that we do is ANF. ANF is a really interesting pass, but let's see what it does. I'm actually not going to do anything, do it the way that I ingest things. So I do it for safety. Yeah, return the same thing. But what ANF does is a really nice algorithm. This thing ensures that if we have some code like, well, I guess if we had some code like f of g of x, right, that this turns into, okay, let g prime be g of x, let f, and then we can finally apply f prime on g prime. And it basically flattens out everything where this function here only takes references, right? So if we had another function like h of y, then we're going to have let h prime be h of y. And then we can take h of y as well. Because again, it just flattens it. We need to do this because we're going to be making a lot of assumptions about the form of Alucard at the end of this. So this has some practical implications, namely all functions, everything really takes a reference or a number, right? Because if we were to take 3, then it would just show up as 3. So we never get any nesting. This is really important. We're going to be avoiding general recursion this way. You'll kind of see that as time goes on. So great, we normalize the expression. In this case, it does nothing because this is already an ANF form. Okay, great. We transform the lets. Transforming let is really simple. It just takes one node and gives it to another. So what we can do is pass transform let. I don't think this really does much. Yeah, it turns the let into hashtag let. This is old. It just changes an IR term. It removes the IR let node, which has like a var and value where it's untyped. You notice that this is untyped into an IR bind, which has a very specific type for the value. So this really doesn't do anything. So this one we can kind of ignore. So let all is interesting. It's not going to do anything here. But again, this just turns everything into lets or returns. So let's figure out what that does. So pass all. We can see here that this had the effect of turning this reference into a let. Notice that we have this last thing being a reference because, we just returned a reference. Like, we don't do anything. But now it gives us let to it. So all this does is check, hey, is this thing a let? Is this a bind or a standalone return? If so, don't do anything. If this thing's a bind constraint, which I haven't shown you yet, but we can do it if we look at, I don't know, what is this? Square root, I think square root. Yeah, if we look at square root, we have a bind constraint. I'll just go through this list and do the same. So, it's very similar to what we had before. And it'll do some work. I'll just recurse over this because this is the same as the top level. So that's all what let all does. So you're seeing that we're doing really, really small steps here. We've really not done anything. We've been through, I don't know, 3 passes. The most significant one is ANF, but since the code mostly is already in ANF, we've really done nothing. So that's, I guess, kind of reassuring. We haven't really done anything. And then we can finally call linearize. Let us call ANF normalized expression. Is hashtag 68 that, let's call linearize body. And then finally, we figure out where we return the last body binding. So the last thing in any expression is returned. So since I turned everything to lets, we're in a really good form. So I guess I'll give some practical implications of this let all. Is the type. We take a constraint list, which is saying we have some type of what I call a linear list. And the way that I diagram the types kind of as the following. We have a linear list. This has only been through linearization of the front end, meaning that I just call ANF on it. And that's all that this type means. And then we go to a type-aware list, which removed all top-level forms which aren't binders. And it's been through ANF. And so I kind of express that through the following. So this is, I guess I'll explain where I am, because this may be confusing that I'm jumping around over and over. I'm in a folder called intermediate. Intermediate is the intermediate representations of Alucard. All these changes we're doing, we've changed it from some top-level data structures into really this intermediate data structure. We can pun a lot of terms because common list lets us or various product types. There is no tag, so I can kind of just reuse most of it, which is a really handy feature. But I guess to show you, I think it was in new terms. No.
Yeah, Jeremy, what do you mean by that? So you can or together types?
Yeah.
I'm not familiar with that.
Sure. So it's very similar to a sum type in ML. However, it lacks tags. What I mean by that is when you make a sum type in, say, like Haskell or something, you say like data list A is equal to cons A list A or nil, right? But this cons is a tag. But imagine we had instead data cons A is cons A and some recursive A, right? You can imagine that there's something around this. Well, then you wouldn't need this cons here. You just say that this cons data is this. It's not a tag, right? This thing really takes a cons. The type of this is really cons. This cons. So the cons type or the nil type, where in the new type nil is equal to say empty parentheses. So you can imagine that we don't have a tag. We just say like here are the contents of it, and they already exist. It makes it so our compiler is really flexible, and I'll show you what I mean. So for the linear term, I kind of sped over what the representation of Alucard is. Doesn't matter that much for how we're kind of going through this series. But for a linear term, it kind of has everything, right? It has term type manipulation, which is an OR type of like term no binding, which is like base, meaning plus. Base is like term normal form, so numbers, references, and application. We have record forms, so like making and defining records. We have array forms, which is like setting, getting, array lookup, array allocate, from data, array set. So this term normal form has a bunch of things in it. Like everything which you see in the language really is still here. So anything you can write in the language, like type coercions or arrays or records, all that exists in term normal form, except for the type manipulation, which is type coercion. All that belongs in what I call term type manipulation. Naming is really bad because I'm just arbitrarily like layering it. Like all this is arbitrary layering, but I can just OR these arbitrarily because if we try to match on this, there's no tag, meaning that when you match over it, it will yell at you in the same way that an ML compiler will yell at you, which is kind of what you want. And so the linear term, so this is before we let everything, anything which can show up on the top level is all these things like plus, minus, array lookup, array set, all that can show up in a linear term, along with the starting binders, which are term binders and SPC, the binders that we created, along with a thing called bind constraint, which we see in square root function. I should have made this buffer bigger, but you can see the square root has with constraint, and that's what this bind constraint is. So all these can show up in a linear term, along with a standalone rep. When we do our transformation, by letting everything at the top, we transform this form, which can have anything at the top, to only having binders at the top, right? Now we've just transformed it where we removed this term type manipulation, meaning that plus times all that can't show up at the top. It has to show up in the binder. And so what this means when starting binder is applied to a thing, it means that this type can show up inside the starting binder. And notice that this is the same as this. So we just moved all these into the starting binders, namely a single bind because we haven't done anything yet. But that's kind of the way to conceptualize the types. We're going to be doing more in the future. Like we're going to end up transforming term type manipulation to term no binding, which I think gets rid of the type manipulators. We'll see that soon. But you can kind of see like this is how I'm layering it. And in order to kind of get a feeling of it, I have these comments up here that kind of tell you what they're kind of used for. Like binders can contain all the things in the language here. They don't contain the type coercions here. That's why it's kind of layered that way. I hope that makes sense. Does everyone kind of get a rough idea of kind of how we're doing it? We'll see the transformations in action so we can actually see it practically. But for now, this is how all the types are set up. Okay, great. Let's jump back, I guess. So that's what all does. This simple function, right, which only checks if it's a top term manipulator, right? This is the only code that really does anything. This one just recurses for bind constraint because bind constraint has extra things inside because it's any equation. This is all this code does, right? It just looks at this, it gensims a new variable, and it great, and makes a binder. That's all it does. It's really as simple as that. But this has a huge implication on the types. So this is kind of a hidden thing in which we're doing. But if you look at the type signatures, you can see that it actually is quite good for what we're doing. So this is part of what I call linearize. And at the end of it, we just return the last thing as we saw. And that is the end of linearize. So we've kind of gone through our first big pass. I call this a pass because linearize kind of handles all this. It kind of linearizes the entire language and puts it in a way so that we just have lets and returns on the top. And on the right-hand side, we have applications or like lookups. As you can see, we have a lookup node here. But the lookup nodes can only really be done on like references because we've linearized it. I can't have another lookup inside a lookup. That's just impossible because of ANF normalize. Because of this, our language is at most recursive 3 in depth. If you discount bind constraints, which are infinitely recursive, but without those nodes, our language is at most 3 depth, right? You have the let node, you have then the term, and then this term can take a reference or a number. So we avoid general recursion in like the vast majority of cases. Okay. So that's the first, I guess, major pass of Alucard, is we just do that, and let's continue along. So we do linearize, and now comes type checking. So into type check, I do a few things. I call check on the circuit. So after I linearize it, I pass it to check. We're going to get into the type checker really soon, but let's see what it does. The type checker takes the body, which is this, and the circuit. So I don't know what circuit we were looking at, so I'm just going to have to go back up. I think it was L2 norm by hand. I think this was the circuit. So here are the two circuits. So I can call check, really redundant name. I would say 75 and 76. So 75 is this one, and 76 is this one. I believe these are the right types. This tells you that we take a type aware list, which is what we have, and a circuit, and we get back two things. So let's just run this, and then we'll go over how the type checking works. Because this is, I think, the most complicated code in the code base is the type inferencer. Okay, so all it does is that it doesn't change the body. You notice that this body and this body are EQ. I can check. So 75, here, I can actually prove it to you, equal hashtag V77, hashtag V75. This does pointer equality. If I do EQ, and they're true. I've done nothing to the body. They are the exact same pointers in memory. But what I have done is have this, what I call a typing context. And the typing context is quite nice. If we look at our circuit L2 norm by hand, we take a 3D point, which is a record of 3 points of all ints. I assume an int size of int 256. I think that's 32 times 8 is 256. I think that's what I did. 256 divided by 8 is 32. So it's like a 32 byte array. 32 bytes is the default int. And I just type check everything. You can see G1150 looks up the X plane. Well, we know that if we assume that if we say int that it has a certain type, then we know this type. So we know that G1150 is an int type of size 256, right? And so we kind of just type check all of this. We know that there is a 3D point which has 3 ints in it. So 256 plus 256 plus 256 is, I guess, 768, right? This thing kind of just does inferencing for us. So this is the next major step, is that we just annotate the types. This works somewhat simply, somewhat not. I implemented a unifier and something, so you can just kind of infer types in most cases. And there's a bunch of code here. Like, this is the most complicated code. I don't know if I want to go over all of it. I don't know how useful that is. But I break it up into 2 steps. No, I don't do it recursively because I don't have to. So this is where ANF saves us, where we can just annotate a term. And then when we annotate a term, we don't recurse to annotate a term. We annotate a term with no binder, because we're always having a binder in annotate term. So I can match on it exhaustively. So if it's a standalone return, I do nothing. If it's a single variable bind, I have a bunch of logic for it. And if it's a recursive one, the binding constraint, then I just call myself recursively. Only time I do it. Here, I just figure out if annotate term no binder gives me back something, right? So annotate term no binder will do some work and give back, like, oh, a type info or a whole condition. I don't really want to go over all this code because it's kind of complicated, but it just is really tedious, I guess. And that, okay, if it's a record and we know the type, well, then we know the type. If it's a lookup on a record that we know the type, then we know the type. If we don't know the type, then it is a whole that relies on that being known, right? So it can kind of just figure it out. So when one of the things are solved, it can solve the others. So you hopefully don't have to put too many explicit types in your code. It should hopefully be able to tell you. I don't I don't add inferencing of top level values yet, but it's as easy as changing this and adding the initial values as assumptions rather than baked in. I don't do everything perfectly here. I do arrays a bit poorly. I have an issue on Alucard, I think maybe issue 20 something. I think I made an issue about how arrays aren't type checked the best. But yeah, that's all I'll cover about the type checker. It's a two-way type checker, meaning I check terms, I add it to a whole list. If I can refine it later, I can backtrack and fix it. And I have some data structure, which you can see here that can do it. It has holes, it has whole infos, it has dependencies, which all these are nil because we've dealt with them. And then like the typing closure, which has all the types of everything. The important thing is we've typed pretty much everything by this point. Does anyone have any questions on this part of the code and why we're doing this or how this works or anything?
Like in the previous passes, you stressed that we avoid recursion.
Mhm.
Is there a reason you're avoiding recursion? Because isn't recursion sort of idiomatic common Lisp?
Well, I have common Lisp is fine. It's technically not guaranteed by the standard, but it basically is. It's not that common Lisp doesn't like recursion. It's more that recursion makes passes harder. In that if I'm writing a pass, let's look back at our passes. If I look at linearize, in particular, let all, or let all. In this code, I don't have to recurse because if I weren't in an AMF form, I would worry that, oh, hey, maybe I have to recurse in the body and maybe something there isn't leaded. So let me try to let it. The issue becomes really rapidly that when you're working over the code and you have to recurse, it makes your top level language a lot bigger, right? You have all these things that could occur, and they can happen recursively. So if I'm trying to flatten out application, I have to recurse in the arguments to figure out if those work. But if all application takes are references, then I'm done. I don't actually have to recurse generally for it through the terms. It just makes your life easier, I guess, is in a sense. I can choose a better pass than that all because that technically is not a good pass to do it on. But let's look at like relocate records. We haven't gotten into this yet, but because let's see. I call relocate records, but I want to do something else. Where is it? To expand array records. Here we go. We do relocate. I guess it is relocate records I want to look at. Expand application. Now, expand application is a good one. So for expand application, this is all the code for doing it. Don't worry what this means yet. We'll get to it. But the point is I don't really recurse much in it. I think I recurse only once. I don't even recurse once. That's weird. I thought I recurse in one of these. But basically, as soon as I see an application, I can just expand its arguments. I don't have to do it recursively. You notice that I just expand argument because it's in a term normal form. It's either a number or a reference. And if it's a reference, then I can just like and it is in my closure. You'll figure out why I do that later. Then I can expand it. What this means is I don't have to recurse through expand application to call expand application again and pattern match on it. I just know that it must have a reference inside. So it just simplifies passes a lot. It may make a bit of extra code, but it makes the conceptual model of how do I do these passes a lot simpler. Does that kind of answer your question?
Yes.
Okay, cool. Cool. I guess let's continue through the passes. We were in type 5, I think. So we do checking, and so that we finish all the way down to type checking. Wow, we're really coming far. So if I were to do pipeline to type check, we've already covered to type check. We've already gotten this far in the compiler. It feels like we've done no work, and yet we kind of have. So that's kind of neat. It returns two things because I want to type this. To type things in common Lisp, I can't use tuples, so I just return multiple things. So I just do that. And you can see that we have IR expanded list, which we kind of already covered, and type checking. Oh, I forgot to do one thing. We should also cover remove type information. Yeah, should also cover this. All remove type information does is if we see, so all top level forms don't really matter too much other than like in the binder, there exists a value. Inside we check for IR term type manipulator. If it is a type manipulation function, we just remove it. This should probably really be a to-do because we have coercion, and we can coerce, like say, a record into a number, and we actually should be doing work for this, right? I just don't at the moment. I'll just accept that you coerce a record into a number, but because of how I do my passes and how I do inlining, I really shouldn't just remove it. But the type manipulators are things like check this against a certain type, which is useless information because we've already been through the type checker, so we can just remove it. And type coercion, which is in the most part useless information, and so I can just remove it. And notice, because we are in ANF, I don't have to recurse. I just know that if the binder has a type coercion, this is the only place the type coercion can show up. So just remove it. So we just map car, the map function, where the terms, we check. If it's a standalone return, it takes nothing, so we're done. If it's a bind constraint, then we simply check it. We handle the term. We copy the instance of the bind with the value being updated to remove, to basically remove the type manipulator. And how they all work is all the type manipulators have a value, so we use the lens. Like type coercion has a value and a type, and type check has a value and a type, so we can just say IR : value to use the lens. And if you don't believe me, when we meta period, you can see that those two have the methods there to get it. So that's all we really do. Oh yeah, just use the lens. And great, now our type is proper. Now we have expanded list, which is just inside binders, it's term no type manipulation. Or term no binder is what I call it, yeah. I know, the naming's really bad, but just forgive me. It's hard to come up with names with all your IRs. Really is. Okay, great. After to type check, who calls to type check? It looks like expand array does to expand arrays. So the next step we do is remove arrays. Our examples didn't really have arrays in them, so let's look at an array example instead. So let's look at what code here has arrays that is properly typed. Let's look at this one, array from data check. So let's kind of look at this. Array from data check, we can see that we have some lets, we have some references, we have some array lookups. Bar is a reference to this, which calls from data, foo36. So it seems to me that, we're taking this data, we're taking foo, which is bound to 35 and 36, we're shoving it in an array, and we're doing a lookup. Forgive this horrible syntax. I haven't fixed the printer yet to make this readable. So that's why this is ugly and not nice. But all we're doing is we're turning foo and 36 into an array. We're looking up the array, and we're checking foo against in 32. That's all gone now because we removed it. Great. Now let's focus on the next set of passes for expanding out arrays. This also isn't too bad. It looks like I have a function called array handle terms. So let's figure out how this works, and that looks like the only bit of work that we do. In order to do this, we have this code here, so we can just pass it. So what I'm going to do is we called this body and typing, so let's just call it deflex. The var is hashtag v82, so we're going to just call this body. And then the context is hashtag v82:1. So we have context and body now bound to the names in this function. So we can just call this code. So that's great. Body context, I think I did that right. We have an array handle terms. So we can just call this, I believe, array doesn't exist. Gotcha. So what is this array package? alu.pass.array. Great. So great. Now we can kind of call this, and we're going to figure out how this works. So let's handle terms. This is going to do a lot of things because I broke this up, I think, into two passes. I forget. how I this is a rather new addition to the code base. Handle terms, I guess, does something simply. It handles term. Okay. How handles terms kind of big. It checks. So we are going to be map carring this because we're folding this. So we're building up two things. We're building up a context and we're building up the term. The context is our typing array. You notice that our typing array is different. Like our typing array before is just this right here, right? Is this right here. We just have G1172, G1, we have the arrays in here. But I'm going to be letting new names for the arrays. And because of this, I want to update the typing context with new values. And so if you look at it, it has a lot more things inside of it now. Like, holy hell, it has a lot more things inside of it. It goes on for quite a while, and I'll show you why. And we've also updated, the body here to be quite a bit different. So that's why we're folding it, because we're updating the context, the typing context, along with the body. So we have to fold. And what's really cool is that I can just call handle term, and handle term will take whatever form it is. If it's an array lookup, it'll handle an array lookup. If it's an array allocate, it'll handle the allocation of array. If it's a from data, it'll handle it. Let's figure out how. Okay, so in this code, handle term only takes a single term, so it takes an expanded term. An expanded term can take a starting binder of term no binding, meaning that we care about the array forms here, because that's all this pass really does. If it's a base or record form, we ignore it, because I don't care. All we care about is the array forms on this pass, so we can ignore all these and just match on the array forms. And I believe I do that. Here. You can see if it's standalone ret, I don't, oh wait, handle terms, it's going to happen inside of here. If it's a base, record form, or array set, I do nothing. So the base is all the basic stuff. It's term, normal form, plus application. If it's record forms, we do nothing as well. Notice that I can also pattern match on a higher level. In ML, you're kind of forced to do the ORs by hand every time you pattern match because you have tags for everything. But here, since I have OR types of OR types, I can be lazy and just say, well, if it's one of the record forms, I don't care. If it's one of the base forms, which is three things, I don't care. But I care about all the array forms. So instead of having to match the array forms, unbox it, I can just match the array forms. I don't do anything for array set because it's a to-do. So I do nothing for array set. I should do this. If someone wants to help me, please help me on this. It's not hard. I just haven't done it because I was rushed for time. There you go. You learned a secret. If it is array lookup, we do a bit more things. Array lookup is a bit more complicated, so I want to cover that later. I want to come from data. From data is really cool in that, we saw it earlier in our syntax. I think, what did we call it? Hashtag V, what was it? I think it was like hashtag V something. I don't know what it was. It's this right here. Let's just copy this because I don't remember what number it is. It is right here. You can see here that we do a get. Oh, this is not. Is this the right one? It's not Elpinor by hand. What we want is array from data check. We can see that we have some reference here. Yeah, we have some lookup here. Right here, we have reference bar 0, but first we turn everything to an array. And so this is the code that turns things into an array. Is that we have a thing called pack. So we have a module called pack. And what pack does is that it can pack things up. Hence the name. And all that does is it calls, did I call the right thing? Pack ref, no, I guess this calls that. Make reference, yes, last result term. Pack final. Does this go into the pack final? Oh, this is not. It's jumping to the wrong location because this file isn't compiled right. Odd. Pack ref. Final ref op. Oh, it does, but it calls something here. Okay, where's the packing logic? Sorry for this. I thought this would have packing logic in it, and it does, but I don't see where. Makes reference. We take the vars. Do we do anything from it? Rebind term. Append term. Let's go back to pack and I'll show you what I do. I'm sorry, I'm kind of confused because this should just be packing it, but it isn't. So I'm confused. Oh, this just takes the final term. Yeah, that's what I'm doing. Yeah, because I already did the code somewhere else here. To array, that's where it is. That's why I was confused. You call to array, and to array is going to be calling the packing. That's why. So we have a thing called packop, and all to array does is that it takes the context and the term. So we're going to, I guess, call this ourselves because we can. I think we have context, and then I have term is what I called it. All right, no, I called it body. So I'm going to get the thing in the body. So we're going to just take the cotter of the body, and we're going to take the IR colon value of it. So we have this from data here. And array takes the context, so we can call, but you notice you can just call any function in my code base. As long as you can like trace kind of how it works, you can just call it. This is important because if you don't understand how something works, which I forget, we can just call it here, 94. This creates a reference because we don't have a body to put it in. Let me, that is annoying. Well, we're going to use a term that we did yesterday. I think I still have X. So what we're going to do is emit with circuit body. We learned this last time. I think emit with circuit body, we take X. Great. We learned this trick from last time. So great. So this creates a reference from data. This should also be... That's weird. Should be calling pack. Oh, to array isn't the to array I'm thinking of. I have to do alu. That's why I was confused. Alu dot array. What is this module called? Pass dot array colon to array. This one's an internal function, so I was confused. Forgive me for my ignorance here. Is not a form piping context. Did I pass it in the wrong way? Context comes first, yes. Live demos, they go badly sometimes. Hashtag B94. Oh, I meant, yeah, that's why. This shouldn't be that. So this should be context. Forgive me for my transgressions. Is not of type new bind. Okay, so we just take the card of this. Great. Sorry for the bad thing. This thing takes the full binder of it, and then it takes the to array. And you notice here that we did some packing. So this is the term that we get out from this one operation. So if we notice, it used to be from data, but now it's this. So how does it work? Well, we can call packed up colon op. Pack colon op checks, is this an array reference or a record reference? It checks the typing context. In this case, we know it's an array. So what we do is we apply array from here. Array works fairly simply. This code is mostly comments because it's not that hard. We take a sequence, right? In this case, we have numbers which are 2 to the 32, right? And what we do is that we times them together. So we take the position. In this case, we have a list of foo and 36. Our foo is actually really 32, right? So we take our list here. And then I index in them position-wise. So we have a list 1, 2, etc., right? You can imagine we have a list 1, 2, 3, 4, blah, 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 right? I think I used 1, 2, and I think I maybe count from 0. And then all that we do is when I map car over this, lambda x index, all I do is it looks at it, I times the element, which is x, by the exponent of xpt of 2 to the index by the data size, which in this case is 32. Yeah, so we take 2 to the 32 and we just like shift it. And so we get like these big numbers, and we should really start from 0. So 32 stays the same because this packs the first n bits. Because remember in the circuit model is a bit interesting in that arrays aren't real. We have to pack this into a single number. So we have to bit shift everything to fit in a single number. And because of that, we can just like kind of do this work. So, you know, exponent 2 to 32 is this big number here. And when we times this by 36, we get this number here. And this number, if we look at the bytes, Common Lisp is wonderful and lets us show it. The first X bits of it, which we can see here, is all zeros, meaning when we add this with 32, so let us now sum the list that we just did. Is sum a function? It is, but apply plus to hashtag v101. We get this number here, but if we look at this number should look familiar. If we look at this, it's hashtag v24, but if we look at 32, it's hashtag x20. So we can see that we just appended this, and if we had the most big fixed number, it would be right here. So you see that we've efficiently packed an entire array's worth of numbers in a single number just by bit shifting it and doing addition. We do this on the Alucard level, and what's cool is that this code's not an ANF, right? If you look at this code, it's not an ANF. But I can call the pipeline. So I call the pipeline all the way down to 2 type check. Because we know that we've coming from a place above 2 type check, we just call the type checker on it. And because of that, all these new terms get added to the context. And that's why we get all these new things in the context right here when we run the code. You know, where we have hashtag G1231, that gets added here, right? Size 32, the type is this. Isn't that neat? So, yeah, we just do that. It just works. I can call the pipeline. So I just called the pipeline. I didn't do some tricks, but I got it to do that. Yeah, and that's all that you need to do for packing, right? You just do that. We get our toArray. This calls toArray, and we're done with the array from data case. The allocate case does nothing. It just adds it to the context with the term of a certain type. Okay, that's not too interesting. From data, lookup's more interesting. This calls lookup, as you can see. Lookup calls lookup at. Lookup at could be for a record or a array, because I want to be able to make records generic and packed. I haven't updated it yet. So we're going to do array lookup, obviously. Array lookup's more interesting, and that the code is a lot more opaque. So I give a really, really big answer to this. Like, here's how to compute it. A good way of visualizing array packing is the following. We have an array, say, 3, 1, 4, 1, 5, 9, 6. Say I want to look up 4 out of this. I want to get 4. Let's say these are all base 10. Let's split the array like the following. 3, 1, 4, 5, 1, 9. I have to break up the array like this. But in circuits, all we have is addition, multiplication. So that kind of represents a problem. So I have to do this. I have to get it like this. So I have a computation here. Now you can take our array 3, 1, 4, 1, 5, 9, 6. We take 2 to the index size. So this is just 2 to 1,000. We add times that by this. So we get this array. And then we add that to an unused mod. The unused mod is 3, 1. And what we're left with after the first thing is smaller array is equal to 3 is equal to 4, 1, 5, 9, 6, and our unused mod is equal to this. Just because if you do the multiplications and you do the multiplications, you notice how I bit shifted them. We're just doing the bit shifting back, and we're just basically getting this out, and then we do another round again where we take the smaller array. We equal this to, we end up getting unused mod, unused array. So we're saying that the first n bytes of this is 1, 5, 9, 6, and then our answer is the 4. We just have to bit shift it multiple times until we get our answer. I know that sounds complicated. It kind of is. It's not very efficient. It's very inefficient. It creates a lot of unknowns. But here is that formula. This mathematical formula. I just implement it in code here. You can see the pluses and the times. We call it equals. The data that we come up with is equal to the exponent of 2 times the thing minus 1. And then I do that here. So that's all this code does. All this code does it. There's more comments in the code itself, but I'm sure you can read it and agree with me that I'm doing this equation and this grabs it. I really don't want to dwell on it because it's kind of complicated and very domain specific. It's less relevant to the compiler, more important that we end up doing it. So if you look at our pipeline and we call, or was it to type check? We've done to type check. We want to now do to expand arrays. And we go back to the pipeline. Yeah, that's all we did, right? We just call array this function and we're done. We basically covered all the cases. We covered all these cases here, which is all the cases. So that's how it works. And you can see that we create a lot of intermediary variables because that case is a pain. And we can see here that we get a big bind constraint because we have to do some weird things. And we generate out the formulas here for the array lookup. This is what the array lookup gives us, by the way, is bind constraint. Gives us this right here, which, as you can see, you can probably squint at it and say, ah, yes, this equals the formula, but we're not going to dwell on it. I even call it smaller array and lookup answer, so you know what the answer is. So yeah, that's how array expansion works. We're done with arrays. Arrays go away. We've expanded arrays. That's as far as arrays live. We take it from the front end, we go it down to array, we expand it out, we're done. We don't have to worry about arrays anymore, ever. So that's how that works, which is kind of nice. So to expand arrays, that's all it does. Lovely. Next is to expand array records. Next thing we got to get rid of is, because all we have is numbers, records don't exist. So what do you think we're going to do? In the record case, they're not real, so I try not to pack them ever. I don't pack them ever, even though I should pack them in the array pass. This should use a bit more work because, again, it's not full. If I put a record in an array, the array code will break because the records aren't packed, because how my to expand array records work breaks everything because it's bad. So, you know, there should be more interplay between these because records break things, and we'll show you how it breaks things. The next thing that we do is, after to expand array records, we call pass expand array records. This takes 2 arguments. This also takes the circuit. Sure. Why not? I believe it takes the circuit first. No, it takes the circuit second. Great. Yeah, this is going to be a bit ugly, but that's fine. I don't think we have any record code here, so should we do anything? Let's go back to our L2 norm example, because our L2 norm example is much more comfy. It's much, this past here is much more comfy, so let's just...
there is a record check function.
Can you say that again?
There is a record check function in the global examples.
Yeah, the L2 norm example also has records. Is noticing if the X plane, Y plane, and Z plane. So we'll just use that one because we were looking at this one beforehand. So we're just going to continue to look at it. Yeah, and you can see here that we just have references and lookups. So, and we also have the closure, which has records still in it, because yes, great. So when we expand array records, you notice that our records go away. Before we have like a reference and we're doing lookups here. And you notice that these lookups go away. All the lookups go away from the code. How does this work? So this is what the job of expand array record does, is that it removes all lookups. Like this lookup, removes it, replaces it with a reference. Anything that has a record, it will even expand out the application of it. Ajinka may be right, and I may need to give a different example because I don't have applications on a record. But you know, we can investigate that when time comes. So we go back to the pass module because that's what pipeline tells us. This code is also really basic. We look at relocate records. What does relocate records do? Oh boy, it looks big. It's 30 lines of code. That's kind of scary, actually. But we can power through it. It takes a circuit and an expanded list and gives us some data type out called rel. Okay, I don't know what rel is, but that's fine. Relocate records it takes a fully ANF-ified term, where only the last form is not a let, and guarantees out an IR fully expanded list along with its closure. Okay, whatever that means. The comment isn't too helpful. So if we look at this code, I make a rel by calling initial closure circuit, and then I ingest. Gotcha. So I just make some initial closure. So what this does is that this takes a circuit, which is, I guess, storage lookup function on L2 norm by hand. It expands out it because the P is a 3D point, so it actually expands it out. It actually takes it and gives it its proper name. If we look up the X plane, it should really be PX plane. And you can see here, after we did the lookup, that the reference became PX plane. Like, I'm showing you kind of the internals, but we end up making this closure here that ends up becoming the reference. So that's kind of neat. We start an initial closure, and we have an ingest function. The ingest function just calls fold, reduces the fold function from common list for folding L, and I just type case. If it's a bind, we call relocate let. If it's a standalone ret, we call make rel. If it's a bind constraint, I just fold again because I should fold. Okay, great. And I make a relocation ret with my term being my term. So let's figure out how this works. All the code is in relocate. So I guess I'll comment kind of on the methodology of this pass file. You see that this pass file is kind of big. It's 368 lines long. But why? What does this pass file really do? It has their passes, but what's a pass? A pass is just the transformation from one thing to the other. But you notice that this code calls into a package called relocate. The bulk of the logic of this is in relocate. I just give a wrapper function which goes over the list of it. Because our terms are not recursive, I can actually, inside my packages, like relocate, handle a single term. I don't have to handle an entire list of terms, because why would I want to? I can just handle a single term and then, use a higher order function to fold for me. And so, for example, relocate let is big, right? But it takes a bind, IR colon bind, which is just a binder, right? I say it's a binder. The binder is of a certain form, namely that it has, this is a fully expanded list, meaning that this binder must have no arrays in it, or it has records arrays. It's a term no binder. Yeah, that's what it is. If we look at what a fully expanded list is, we just jump to expanded list. Expanded list is fully expanded term. Fully expanded term has binders along with standalone ret. This is, yeah. So it just tells you what's inside. Sorry, it should be an expanded term. So it should have term no binder, which has, as you would expect, as we looked at before, records, arrays, base. Pretty sure that's what I'm working on. Pretty sure that's what it is. Yeah, it's an expanded list and not fully expanded. This comment's out of date. Trust the type signature, not the comment. The comment is less accurate than the type signature I give because I forgot to update it. But yeah, because of that, this make rel, it takes a binder, right? But we know that the type of the binder is an expanded list. And so when we do pattern matching on this, we just look at if it's an array, we do nothing. If it's a number, we do nothing. That's all. I know we got rid of an arrays, but I haven't updated the type. I didn't make an intermediary type between arrays and records because I want to maybe move them around. Maybe records should happen first. Maybe arrays happen first. We know for a fact that arrays happen first, but I want to give the code a little bit of wiggle room if I want to reorder my passes. So that's why I don't assume arrays are gone. That's all. So what relocate let does is that if we have an application and we look it up from storage, and if the storage function is a cons, so I'm checking, I guess, I fully expand the return value of the function. So for example, let's look at a function. So L2 norm by hand. This should be a good example. We look up the name from storage, L2 norm by hand, and we call expand. Do I have expand in scope? I guess I do. Full return value. This takes a name, so maybe I can just pass it L2 norm by hand. That'd be cool. It's just an int, right? We just get back an int, but if something returns not an int, let's look at our file here. It returns, say, a record. We'll know better. Here we go. Arg circuit input. Arg circuit input. Notice we get back a list. We get back an A list of the mapping. In this case, it's like a nested thing where it's a plane. And God, the way that this is formatted is horrible. There we go. It looks like this. Much better. Inside plain, so we have a nested list because the type of nested is plain with X. We get back a list. We get back an A list. We're inside plain, we have X and Y. Inside time, we have X and Y as well. So we get back a list. Notice before we get back just a single int, but if we have a record, we get back an A list of the mapping. Oh, hey, this thing has a plane, and then it has X and Y inside. Cool. So that's what that does. So if this thing is an EXP, so if the cons, then I know that we have a relocation going on. There may be better ways of doing this. For example, since we have type checking now, a much better way of doing all this is just look at our closure. But this code is written before I had a type checker. So this code can be greatly simplified. If anyone wants to work on simplifying it for me, it'd be as easy as taking a type closure instead and checking if it's a record type rather than like checking the function from storage and basically redoing type checking. So I'm just redoing type checking, basically saying, oh, hey, is this thing a record that we called? If it's a record, then, we insert the name because the binder has a name and a value. We insert the name into our closure because we're going to have to update it. And I kind of give the layout of the closure here. If something is a point here, the ref point here gets added like this. So you'll see that, like, in this case, we would have something like this, where, the plane goes to phi plane. The point would go to phi point X and phi point Y. I hope that kind of makes sense. Like, we're just taking this and we're, like, naming it. And we do this for all the terms. So for a record lookup, we're basically redoing type checking again. All this is redoing type checking because we didn't have a type checker. So this has to be rewritten. Basically, I check if the lookup of a record is itself another value, well, then great. I make a relation with the proper names. Either way, I'm going to probably just remove it. So if I have a lookup, I think I remove it here. And that's why when I call this code, this lookup here becomes just a reference. So I check if it's in my closure. If it's in my closure, I replace it. You can see that somewhere in here. If it itself is a closure, then replace it with more let forms. I just do this over and over and over again for every single term. And that's why this code is really big. This function is really giant because I didn't have a type checker. But now that I have type checking, we can just do this better. So if anyone wants to help me rewrite this long function that does not much, please help me. That'd be lovely. And that's all that code does. Right? It's a bunch of code that just basically says, hey, if this thing's a record, replace it with its constituents. We're not going to do application here because that'd be extra complicated. So if this thing is a lookup, replace it. If this thing makes a record, replace it with its constituents. And so we get out a closure out of it along with the circuit, right? So that's all that really happens. Great. And we just wrapped it in this 30 lines of code. And then we expand application. Expand application works as you expect. It checks if we have a relation and we have a function. If we have an application term, expand term, expand argument, expand app. There we go. I call expand argument. The argument checks if it's a reference in my closure. If it's a reference in the closure, what does it expand to? So if I know what it expands to, I just replace it with what it expands to. Like if I pass a record, then it expands to 4 arguments, for example. And so that's all what this does. And after expand application, all that goes away. And yeah, you get a list without records. At the end of this, we have a fully expanded list. I think this is bad on me. I want to actually replace this with a expanded list. It is fully expanded by the end of expand application, but because I want to move these passes around, I want to have another pass which just finalizes it, which has the signature fully expanded list rather than putting it here. But the good thing to know is by the end of expanded records, we have a fully expanded list. So we've expanded out records, we've expanded out arrays. The strategy for records we've discussed. The strategy for arrays we've discussed. Array does packing. Records don't exist. We expand them. We inline them, which breaks API compatibility in many ways, but it expands them no matter where it is. And the last thing we do in expand array records is we also remove void bindings. Void bindings are very basic. They're like functions which return void. So let's figure out what functions return void, and let's see if we can if we call it anywhere. Do I call void anywhere? I have a function called silly range check and constrain. Do I call constrain anywhere? If I don't call constrain anywhere, okay, cool. I have a function called use constrain. So let's look at that example. Where do I do values? Here we go. To expand arrays. So the thing is when we call constrain, here we let a reference G1342 be that. This is kind of bad though, because constrain returns void, right? Constrain returns void, meaning it returns nothing. So what this last pass does to expand array records, last thing in expand array records does is remove it. So if we do to expand array records, it just changes this to a nil. It says we return nothing from this. So make this nil. Also, you notice that in this case, this actually shows off other expansions. This actually shows off because constrain takes a nested type. Foo is nested. We expand it fully in the application. So we actually get to see the behavior of, oh, hey, look, the expand argument literally does expand the argument into its constituents here. So you can see that at work. And we can also see that the remove void bindings just removes void bindings, which again, the type checker would help here. The type checker would tell us we have a void type, but because we throw that away, I have to do some checks, and it's this big pass right here, which is like 40 lines of code. And it just checks, hey, if this thing is void, then make a multi-valuable bind with the vars being nothing and the values being this. And I'm also going to insert in my tree that I remove these bindings. So if I reference them in a return, change the return to return nothing. So I just remove the return in this case because I return a reference, but that reference doesn't make sense. So I just make it nil. So this function has no return type because the last value in it is void. And so I just remove it. And that's why I have remove standalone return here. I end up checking my set and I see if the value is in my set, then nil. So and that's what I do. It's a lot of code because again, I'm redoing the type checker because I didn't have a type checker until recently. We can subsume a lot of this code with type checking codes. If anyone wants to do that, this code can probably be cut in half because we can rely on the type checker to just be like, oh, hey, is this void? Oh, yes. Okay, great. So yeah, I just throw away the type checker at this point because I don't use it anymore. And that's records. We no longer have records. We're actually pretty much invalid vamp-ir. What's left isn't difficult. We're basically at the end of the compiler. It feels like we've done no work, right? There's a bit of work that we did for arrays. We had to pack arrays, and that was kind of confusion. We had to do type checking. That was also kind of complex. And we had to expand out records, which I think isn't too bad, but had a bunch of redundant code. But we're almost done. All we have is numbers left in the language, right? At this point, our number of forms is really small. We can see here to expand array records, we have a fully expanded list, which, as explained before, all we have is a fully expanded term, which all we have is the binders, the standalone ret, and the base. The base just has normal forms, meaning numbers and references and applications. There's nothing in the language left. We're done. So we're kind of on our victory lap. So we're going to, I guess, gloat by finishing up the code because there's not much left. That's really all that's left to it. After expanding array records, I turn it into a primitive circuit. So we can start running this code, I guess. Let's go back to our L2 norm example because I like this L2 norm example. So what we run is pipeline to expand the array records. I'll have to do a lookup. Yeah. Storage lookup function. Great, we have it. We looked up the function. All our references are expanded. We just have our numbers left. Now let us call pass. I don't have to do double colon. A primitive circuit. Thank you, autocompleter. This gets long. I don't like reading long code. I can't read this. There we go. Cool. This also takes the circuit as well. So I think the circuit comes. What does it say? The circuit comes second. Great. the next thing we do is we're going to shove it in this function to primitive circuit. Let's just see what this does. Hopefully it's not too much code. Great. We have a circuit here. So what I'm going to do is I'm going to make a prim circuit of the name of the original circuit. So we see here the name is L2 norm by hand. So I make a data type. We can see the name is L2 norm by hand. We're just going to leave this open here. Okay, so we fill in the arguments. Okay, because notice that the arguments are filled in, but how do we fill in the arguments? I look at it. Again, the type checker could help here. Again, I do a bunch of redundant work because I don't save information. Like, I don't cache the expansion. But I have some functions which do it. I take the circuit. I fully expand the arguments from the circuit. So again, we have the circuit here. Let's just call some of this, you know. Fully full arguments from circuit. We get this, so we turn the arguments into the full version, which is just the expansion. So I have a data structure called expand, which just says that this thing's expanded. And then I have another function, expand, argument name, argument names, and this just takes this list of expansion. So it checks if it's expanded. If it's expanded, it gets all the names out of these, which we can see is X plane, Y plane, Z plane. I throw out the types. So that's kind of neat. And so we just get the names out of it. Okay, great. We have the names of the circuit. Okay, wonderful. We have the names for our circuit function. So this just fills it out. We copy the instance of the prim circuit and we fill out the arguments. Great. That's why this has the argument names. Okay, what else do we fill out? We fill out the output. Okay, that's kind of easy. How do we fill out output? I check the return type. I have a function called determine output variables. This thing figures out from the body. It checks the last thing in the body, which in our case is like this reference here to the standalone ret hashtag G1372. And in this case, it just lets that be the return value. So I just look at the last thing in the list. That's all this does, I'm pretty sure. Yeah, it filters everything if it's not a standalone ret, and then it just takes it. It just takes the vars from the standalone rets, and those are the return values. Okay, simple. It doesn't do much. And that's what the returns are. It just is what the return thing says it is. Okay. Great.
Why are you doing a map can there?
So mapcan is monad in Haskell for lists. It's because I may have multiple, because technically the type dictates that there could be multiple return standalone returns. We know for a fact there isn't, but I humor it because a standalone return may have multiple names in it. So I just say, well, if I have multiple returns, I guess I'll take all the multiple returns. Because I could imagine that maybe a pass maybe makes another multiple return, and maybe I should respect that. I could just as easily said last and then asserted that it is a standalone return if there is a standalone return. So there could be no returns to n returns. So I just map can it.
Okay.
In this case, there is one return because the standalone ret just returns G1372. And because of that, we just return G1372. And the body is just the body. There you go. We've made the primitive circuit. Done. We're to primitive circuit, and then I just rename it. All the rename does is really basic. Rename. Again, this goes probably a bit more recursive than it has to, but it goes through all of the code, and if it sees a reference, it just changes its name. I can automate this a bit better these days, and maybe I should, but I just check everything, and I check, okay, this name, we have a schema. If it is if it's hashtag dash, it should be underscore. If it's and, it should be v. If it's percent, it should be v. Okay, there you go. That's how I do my renaming scheme. I just rename that way. So yeah, it's kind of cool. So let's just run the pass, I guess, because we're based on the victory lap. Pipeline. We then call, okay, so we just call pass on this. Pass rename primitive circuit. Oh, because yeah, this wasn't where I did it. No, where was it? Cool. Parents name. Great. I rename all the variables. You can now see the variables went from like ampersands and all that nonsense to like, I don't know, named properly. Underscores, dashes go to underscores because a vampire doesn't have dashes, I don't think, in variable names. So I renamed those. And you can see that we're kind of already seeing the vampire code out of this. It's just my printer is really bad. So let's us just fix it by calling the last pass in the pipeline. Pass circuit to alias. I think that's literally all I call. Okay, we're done. Notice we basically called pipeline at this point. Notice that this reference just becomes a let. This let G1. Okay, 1 second. I want to actually make the names work for us. So we're going to do that. And then I'm going to hashtag B126. Great. Notice this G1400 becomes this G. Notice I'm just changing what the printer does. Oh, hey, this reference is this thing. This exponent is this thing. This reference is this reference. This reference exponent is this exponent. This plus is this plus. This square root is this square root. This GVG1408 is this, and we return it. That's all we've done. We've just changed how it's printed by calling circuit to alias, which does almost nothing, mind you. It just has a bunch of code here. It's about 111. It's 111 lines of code to just take this code up here into this. And it just does a few things. It just maps. We take the term, we turn it into the vamp-ir equivalent. So we take the term, we just map it to an alias. So we make an alias from all the terms because it must be a standalone red or whatever. I guess I make an alias for it. The arguments are the arguments. The return is the return. And then the body is constraints. So, you know, we take the body, I check it. I eventually take it. So you see how we're map canning this. If it's a standalone ret, we do nothing with it because we don't care. If it's a bind, we turn it to a bind. If it's a multi-value bind, we also turn it to a bind. If it's a bind constraint, I do this recursively because that's the only recursive function in my IR currently. I'm going to add loop, which is another one. There's no application here. That's why this doesn't complain. Yeah, it doesn't complain. So there's no application. Term constraint is somewhere. It just takes it and makes terms, right? This code isn't complicated. You can look at it at your own time, I think. It just maps things to the vamp-ir data structures, which I store in vamp-ir. I have my entire, I have a standalone spec for vamp-ir where like I just map what our existing spec was to the pipeline to the spec here, which has like constraints and statements and expressions and primitives. Someone was asking, I think last session, about the ANF for it. I make my own basically through these OR types. So if you're curious about how I view vamp-ir, I have these OR types for it. And I just fill this in. And the printing here, I'm not actually printing. I click on this. This is actually common Lisp code. This is a common Lisp type. This isn't vamp-ir. It just is a representation. It's just a printed value of it, but this is my real code. And I do that finally through, I think here, I literally have a big comment here that says, read this before you understand the code, because I use format, and this code looks really weird if you're not used to format notation. This code will look really weird, but this code is responsible for printing it nicely. So this is the nice printer. So you make a nice printer. It actually is understandable if you read this comment up here. So if you read all these comments, you can kind of like, oh, well, that's how it works. Otherwise, it's going to be like, what the hell is this? What is this A2:I nonsense? I don't know. But if you read these comments, it makes sense. So it's a format rundown for those who are unfamiliar. And yeah, that's the entire compiler. This is how we get from pipeline. Pipeline. That's how we get from our function here. L2 norm by hand. All the way down to our code. This code becomes this. We looked at every single step of the way. We saw how records expanded. This one had record expansion. We saw how arrays got expanded. We saw how we ingested things. We even see how we print. I kind of skipped over how we print things, but it's like really, it's not that hard. It's just you have to understand what format does. I don't really feel like giving a lecture on format. I can make another video for that if anyone's curious. because it's really fun. I had a lot of fun with it. But yeah, we saw all the intermediary stages of the language all the way down to the bottom. I'm going to probably rewrite my printers for the old functions because they look ugly. This hashtag V looks horrible and it's not readable. So I'm going to probably make it akin to looking like this at a later date. So it's more obvious how this relates to this. I'm going to make these have almost the same printer when I get around to it. And so that way you can see how things transform in the compiler in an easier way, rather than having to read this hashtag V nonsense. Did anyone have any questions? That was the entire compiler of Alucard. That's all the code. And notice I ran all of it piecemeal, function by function. If you had a question about it, I would have just ran a function that did your question. And you can do this yourself, basically. It's not that difficult. You just follow what the pipeline does and pass things around. If you have a question about like recursive functions and why they break, like inside check, and I was like, let me change the compiler because CCL is better at giving debugging information. In package LU test, like if I wanted to like say in my unifier, whoops, break something, like say, oh, I have this here, let's break. I can, and then when I do my pipeline on the L2 norm, I can actually see variables. So a good thing for debugging is what is the context at this point? I can actually do programming on this because this is not text. So if you have any questions about even how like functions work, you can just insert breakpoints or stickers if you're using Emacs, which allows you to trace what values are over time without breaking your code, and like step through it over time. You can, you can just dump everything to the REPL and play with it. The code base is meant to be very interactive. Continue. Don't care about any of those breaks. So you can just recompile code and check it. We have a test suite. I have a code coverage function here, which should work. I figured out I broke it at one point, but it works. This creates this, which gives you test coverage. If you're scared about the lack of typing in Common Lisp, don't worry. I test literally almost everything. So if you're worried about, oh, hey, I want to test some code, well, this tells you what isn't tested. So great. That's the entire code base, though. Like I skipped over like the types and the data structures, but you can look at that yourself. That's not hard to understand. It's just classes records, really. And I skipped over unimportant details, but you know the process now. I guess I'll stop rambling and ask if any of you guys have questions about anything on the compiler.
Oh, thank you, Jeremy. Yeah, that was a lot to take in, though. So
yeah, I apologize. I kind of rushed.
Digest.
Yeah, sorry. I kind of rushed through the rest of the compiler because it's not hard, right? It's just we do some passes. What passes we do? Yeah, we do some work, but the compiler does almost nothing, I would argue. With that said, the compiler does nothing, but there's too much code. You can see here that I have about 3,000 lines of code. A lot of comments, but too much code. I think I can probably cut this in half if I was being smart. And since I have a type checker now, I can do a lot less work. The compiler has a lot of work to do. If we look at my issues, I have a bunch of issues. Some of them on like good first issues, like gensim all let bindings. You notice I don't gensim enough. That's bad. Remove binders to void. The code can be done better, is what I basically argue. The code can be done better. I have a bunch of stuff here. If anyone wants to do any work whatsoever, I will be more than happy to pair program with you on any of this. The language can be improved a lot. There's a lot of things which I consider bad about the language in terms of how it's implemented, and I'm just kind of too lazy to do it. But if I do it with someone else, that makes it a lot easier because I can just here's my thought process. We get you used to the code base, get used to playing with the language. Yeah, all this is like not that bad. 4,000 lines of code with I think half of it in the type checker. The type checker is like 800 lines, and passes are like 1,000 lines. So you see that like the type checker is big as the passes, and the passes don't do much. This is really the bulk of the language. There's other things, but if you're curious like on how big the project is, it's not all that big. It's there's a bunch of stuff in it, but it's not that bad. even the vamp-ir printing code is like 354, and like half of it I don't use because the standalone is like 161 lines of that, which I don't do anything with. So yeah, like this code isn't. I hope it's not that intimidating to work on. I hope it's a kind of a friendly code base. Things are just abstractions and layers. Thank you, Jeremy. Cool. I'm gonna stop the recording now because I think that covers the rest of the compiler. So I guess thank you for everyone watching as well. This is, I guess, the last part of a 2-part series. I didn't know how much I can get through. If everyone wants any, like, request any videos about certain parts of the compiler, like I skimmed over the type checker and I skimmed over the packing. I skimmed over record stuff. I can just make a video for that because videos are easier because I can just like jump to code and like talk over it. It's much better than writing. You get a feel in video format, whereas in writing, it's not possible to get a feeling. Like I have to explain in a lot of words how you interact with the system and how it works. So, bon voyage.